Thank you for coming to my talk, AST-Groovy Transformers, more than meets the eye. So the first thing is, don't worry, this is a beginner talk. I'm not going to create an AST transformation, but I'm going to show you a lot of transformations that Groovy provides us out of the box that help us a lot when we develop with Groovy. So this talk is organized at the beginning. I'm going to explain a little bit of theory, just a little bit about what is an AST and how it works. And then I'm going to show you the main AST categories, and I'm going to explain some of them. For some ASTs, I'm going to show you, I'm going to explain how they work, and I'm going to show you some examples, and for the others, I'm only going to explain because there are a lot of them, and I will need something like 2 hours to explain all of them. So first, very quickly, let me introduce myself. I'm Iván López, on Twitter. I work at Kaleidos. We are as a Groovy developer. We are a technological company based here in Madrid. Also, we have opened a new office in London. I'm one of the usual suspects of the Madrid Groovy user group. We meet up the first Tuesday of every month. So if you come to Madrid sometime, please send us a tweet and join us. And well, I'm also one of the guys behind this conference. So let's start. I want to start with this quote. The best code is not codable. Because us developers are lazy. Don't pretend that we are not, because we are lazy. If we can solve a problem just writing a small piece of code, we go with that way. So less code also means less bug, and we need less code to maintain. So with this AST transformation, we can write less code. So now the theory. Groovy provides us 2 different kinds of metaprogramming techniques. Runtime metaprogramming and compile-time metaprogramming. And in this talk, I'm going to talk about compile-time metaprogramming. It's an advanced feature that is useful in some situations, and some frameworks use it. And it allows us to analyze our code during compilation and modify the final bytecode that the compiler generates. And when you are developing an AST, what you're finally doing is writing code that it's going to write bytecode. So when the Groovy compiler reads our source code, it redefines and creates an in-memory AST abstraction stream that represents our code. And during the different phases of the compilation, the compiler will rearrange the nodes on the tree, add new nodes, and even remote nodes. And on the final steps, this AST, this tree, is converted to the final bytecode. So with this kind of metaprogramming, we can hook into these phases to modify this tree. So finally, we are going to modify the bytecode. And this is the really important thing is that it's bytecode. I mean, it's not runtime metaprogramming. We are generating bytecode, and it is cool. And also, the Groovy provides us 2 different kinds of ASTs, global and local. The global ones are applied to all our code during the compilation, and we don't need to do anything explicitly in our code. When we create a global AST transformation, we create it, define a meta information file with all the information about the AST, and just put this jar into our class path, and it works. And for example, brains use these global ASTs for dorm. And Groovy doesn't ship any global AST out of the box. And the local ones, we need to explicitly annotate the code. So we don't need to create a meta information file. They are local to that code, and they are more easy to debug sometimes. And unlike the global ones, the local AST transformation may support parameters. So let's talk about some of these out-of-the-box transformations that we have in Groovy. These are the categories. please don't pay too much attention because I'm going to explain some information in these categories. I'm going to focus almost on code generation and class design, but I'm going to show you transformation for the rest of the categories. So the first one is code generation. Inside this category, there are include AST transformation that help us to remove boilerplate code. It's typically code that we need to write, but doesn't carry useful information. It's just boilerplate. So the first one is to a string. With this annotation, this annotation will implement for us the toString method. And if you have read effective Java, you will remember this item number 10 that says that it's a good practice to implement this method. Because if you do not implement the method, you can create this class. You have a user class with a string, with a name and an age. Then you create an instance, and finally you print the instance, and you will get something like that. The user, the name of the class, and the memory address. And this is not useful. You can see anything about the instance that you have created. So what you can do is annotate the class with a toString, and now if you create an instance with name Iván and age 35, you can check that now you have this nice implementation for toString. It will print the name of the class and the values of the parameters in the natural order. I mean, the order in which they are defined in the class. And what this transformation is doing under the hood, it's creating something like this. It will implement our toString method and create a new string builder, add the name of the class, the parameters, and this is not the real code because they use some helpers and check for nulls and some kind of stuff, but it's pretty much the same. And another cool thing that you can see is that actually you can, with the Ruby console, you can see this code. You can open the Ruby console, copy and paste that code, annotate it with add toString, open the AST browser, and you need to select which phase of the compilation you want to be on. So this toString transformation is applied for the canonicalization phase. So if you check that, if you select this phase, you will see in the AST browser that this code that is generated. And this transformation can be customized. We can exclude properties, include one, ignore null values. So for example, we can customize the transformation, including the names of the attributes and excluding the attribute called name. So now if I create again the same instance, it will print the attribute, so now age, but as I have excluded name, it will not be generating or printed in the implementation. Another transformation is equals and has code that will generate this implementation for us. And remember, I'm going to talk about effective Java in some of these items, because if you remember these items, it is not always that easy to implement equals and has code. And also, once you implement equals, you should implement has code, because if you don't do that, your code is not going to behave well. You are going to have some strange behavior. And that's the reason, because we have this equals and has code annotation, and we don't have one at equals and another one at has code. You need to implement both methods. And this annotation, it's not always easy to implement these equals, so this annotation do all the hard work for us. So, because a good equals implementation needs to be reflexive, needs to check for symmetry, transitivity, consistency, and non-nullity. This is what Joshua Block said in this effective Java book. And you should use the same fields for equals and also for has code. So if you have this again, our user class, we annotate the class with equals and has code. We create two instances with the same values, and because we are implementing these methods, we can check that both instances are equals and their has code is the same. And what the Groovy compiler is doing is something like this. All this code, and please don't pay too much attention. I don't even going to let you see this code, because when I see all this code that we need to write in Java, I only think of this. I'm terrified. I don't want to write this code anymore. So thank you, Groovy developers, for writing this annotation. Actually, I was looking in the source code, and I think that was Polking. He was the guy that created the annotation. So if you meet with him sometime, please pay him a beer on my counter. And you can also customize this annotation, excluding fields, calling the super, and so on. For example, we can include only the name property. So if we create two instances with the same name but different ages, they are going to be equals and the same implementation for the has code, because we are only taking care of the name attribute. And the third one is tuple constructor. It will create for us some constructor that are very useful in sometimes some notation for when you class some parameters. So again, we have our user class, annotate with a tuple constructor, and we create an instance. And this is the default map constructor with the named attributes and the value. Nothing new here. But then we can create instances just like this. User, Iván, and 35, and user with only the first parameter, because it's using the same natural order in the class. And what this annotation is doing under the hood is this. It will create a new constructor for us with all parameters initialized to the default values, and just assign them to the private fields. And again, you can customize this annotation with all of this stuff, including some properties, excluding, and so on. And as these three annotations you usually do or write or use the three together, you can just use a canonical. That is a meta-annotation with these three to a string, equals and has code, and tuple constructor. So now we can annotate the class with a canonical, and if we create a new user and check the toString, it will be valid. It will be this one because the toString annotation is applied. Then we can create a new instance with the same parameter using the one of the constructor with the tuple constructor annotation, and then we can check the has code and the equal, because this annotation has also been applied. Okay, having constructor. This annotation is useful to reduce some boilerplate code when our parent class has a lot of constructors. It's useful, for example, when you override exception classes, because the exception used to have more constructors. So if we create a new exception and annotate this class with inherit constructor, it will create this annotation will create for us all of this constructor with all of needed parameters. So if you don't need all of them, you just put the annotation and you're done, or you can override the constructor that you want. Okay, lazy. With this annotation, we can lazily initialize some fields of our classes. And it's useful when we create classes that has extensive resource, because sometimes if you don't annotate this with a blessing, you will initialize all these expensive resources when you instantiate the class, and sometimes you don't want this. You only need to create the class and postpone this initialization until these resources are used. So with this annotation you can do this. And effective Java talks about this in this item 71, and you can check what are the useful cases for this annotation, because you shouldn't put this lacing in all of fields. And if we have this class and we annotate this linked list without lacing, when the Ruby compiler, with the annotation, will do something like this. It will remove my field and it will create a new one and override the getter method for the old method, so for the old property. So until we use this field, until we execute the get method, nothing is initialized, and when we get the field, it will be initialized here. Another annotation is adsortable. It's an AST transformation that is used to help write classes that are comparable, and they are easy sorted by numerous properties. So this annotation will implement for us the comparable interface, and this is cool because there are a lot of algorithms there that use comparable classes to sort your instance. So you only need to annotate your class with this annotation and you can now use all these algorithms. And this annotation it allows you you can customize this annotation with a lot of things. And another thing that this annotation do is create a lot of comparators for you. So with this class user, with name, age, and born, if you annotate the code, the transformation will do this for you. First, it will create or it will implement the compare2 method with, again, the natural order. First the name, then the age, and finally the born. And it will also create comparators for every field. So we have here a name comparator and an age comparator. And with this code, we can write something like this. We create a list of users with name, age, and born. And then we can use these comparators. User, comparator by name, and check that the names are sorted. And we can also use comparator by age and check the born date. And we can customize with include and exclude. So if we exclude the age and we try to execute again the last line, it will throw a method missing exception because this comparator has not been implemented. Builder, another useful annotation. With this transformation, we can create instance that will be called using a Fluent API. So this transformation supports multiple building strategies, and you can even customize or use your own implementation. You can set the builder name, exclude properties, include them. And this is useful, for example, when you have a class with a lot of parameters, because it's not very clean code to have a class or a constructor that affects, 8 parameters. So with this annotation, you can write something like this. You have again this user class. We annotate with a builder, and we have this new static builder method. And we have this with the default strategy. We have these new methods: name to set the name, age, born, and finally we have this build method that will create the instance. So finally we can check that these values have been saved in the instance. And you can customize this name. These are the default, the same name for the method as the fields, but you can change this behavior. And what the notation is doing is this. It will create a static class for the builder, and it will create all these methods for every property, in which, for example, here we can just store in the board date and return the instance to be able to chain all the methods. And finally, the build will just instantiate a new user, set the values, and return it. And now I'm going to talk about these class design annotations. These categories of annotations are aimed at simplifying the implementation of well-known design patterns such as delegate, singleton, using a decorative style. So with delegate, we are going to implement this delegation design pattern, and we are going to delegate the calls in the instance to the delegated properties. And what this annotation is doing is promoting or delegating all the public methods in the delegated field. So let's see with an example. We have this event with a date and a name, and we can create two instances: event Greach and when, April 10th, 2015, and then we create another one, Greach.conf, June 2nd, 2015, and as the local date property is delegated, we can write this code. We can say that Greach is before the Greach.conf. And this works because this annotation is doing this. It will delegate, it implements all these public methods for the local date into the class. So when we execute Greach is before, it will just execute this method in the when instance. Immutable. With this annotation, we can create these immutable classes. Nowadays, with some languages like Clojure, you have this immutability password. So, if you remember, for effective Java item 15, to create an immutable class is not always that easy. You have to take care of some rules for immutability, so you don't need to provide mutators to change the state. You cannot override methods, so your class should be final. All methods should be also final, should be private, and you should optionally implement equals and scope and to string. So with this annotation, we can just write this code, annotate a class, create an instance, and this annotation will generate all code to implement these immutability rules. So if we try, for example, extend our user class, this will not compile because now our user class is final. And if we, for example, try to change the value of the name, it will throw this read-only property exception because it is not allowed. And you can check all these rules just with this annotation. MOIs. With this annotation, we can simplify catching some values. It is not a cache like, for example, AH cache or Spring cache. It's more than a local cache, and you need to be aware that you can't remove values from the cache. So you can only use this annotation if for the same input you always get the same value. Because if not, it is not going to work. So the classical example is the Fibonacci. It's for every number, we have two recursive calls with the previous values. And these kind of algorithms are useful or we can use this annotation with these algorithms because whenever we calculate a new Fibonacci number, we are going to need to calculate all of them multiple times. So I did a test in this laptop, and without the annotation, calculating the Fibonacci number for the number 40, it takes more than 10 seconds. And then I put the annotation and try to calculate the Fibonacci for 300, and only took 13 milliseconds. So it just executed and done. And without this annotation, the Fibonacci of 300, I don't know what it takes. Maybe 5–10 minutes, I don't know. And another example, this is the book example, the Fibonacci. But another example is this. We were writing a migration tool from Taiga for Redmine to Taiga, and for every issue in Redmine, we need to get all the user's information to send all this data to the Taiga. So the thing is that when the Redmine API doesn't expose or only expose the user ID when you read the issue. So for every user or for every issue, we need to get all the user information, and this method will make a lot of calls to the backend, to the Redmine server. So what we did is just annotate the code with memoize. So the first one that we need the data for the user ID 42, it will go to the server and cache this result. And the next one, this method just return the value, the cache value, without going to the server. So no many improvements. With this With this annotation, we can integrate. Oh, come on. I'm going to use the table. Okay, let's see if it works. So with this annotation, with these categories, or in this category, we can integrate with the most widely used common logging framework. So we have these annotations at log4j, at log4j2, and slf4j. And this annotation without our static final field for the logger, but we need to be aware that they don't add the dependency, so you need to put the logging framework on the class tab. So we can write this code, just annotate with, for example, at log4j, and then just write log the book, whatever you want. Then we have this declarative concurrency. With this annotation, we'll simplify common concurrency patterns using this declarative approach. And inside this category, we have these annotations, synchronized, at with read log and with write log. The first one, at synchronize, this transformation works very similar way that the synchronize keyword, but it locks on different objects for a safer concurrence. And it can be applied to a normal method or static methods. And with read log and with write log, we can synchronize when we are reading or writing code some variables using these threads. Then we have cloning and externalizing. With these two annotations, facilitate the implementation of the clonable and externalizable interfaces. We can use autoclone to implement this clonable method, and this annotation uses some strategies. And for example, we can always call the super.clone, or we can implement a new constructor and copy the properties. It has a lot of configuration. And with this auto-externalizable interface annotation, we allow us to add these two classes that we need these two methods that we need to implement when we write external and read external method when we implement this as externalizable interface. Yeah, safe scripting. As you know, Groovy is a great language for scripting, and it's very easy to write an application and allow the user to write some code and just execute inside your application. But you can do this just like this because I don't trust the user. So if I let the user to write some code into my application, it will block my application, it will eat all my CPU, it will crash my machine. So with this safe scripting annotation, we can just prevent all this stuff. We have this three annotation with upthreading the root. As you know, it's not possible to stop a thread in Java. You can check or you can set that you want to stop the thread, but the JVM will stop it or no, and it's not possible for you to stop a thread. So what this transformation is doing, it will check this interrupted flag and some places in the code when in the loops it's while and for, and in the first instruction of the method and closure. And if this flag is true, it will throw an exception to abort the execution. With timing the root, you can abort the execution of a thread after some time. You can annotate a class with timing the root, for example, with 5 seconds, and if the execution took more than these 5 seconds, it will be aborted with throwing an exception. And the last one, a conditional interrupt, is used to interrupt an execution of an script with a custom strategy. You can, for example, implement a very simple management resource. And for example, you can annotate the script and imagine that you are calling an API and you only have 10 calls per minute. You can annotate this code with this conditional interrupt, put there your logic, check the number of the calls every minute, and once you reach the maximum, just throw an exception and send a message. You are not allowed to execute more API calls. Now, compiler directives. These annotations have a directing path on the semantics on the code, instead of just generating code. So with this annotation, we can change the behavior of the compiler of the program at compile time or the runtime. We have these three. These are the most important. And type check will enable the type check static analysis. It will analyze our code, our dynamic code, and we'll get errors during compilation. But this annotation doesn't change the behavior of the code. our code will be the same with this annotation or without it. Then we have at compile static, that it will enable the static compilation of the code, and the generated byte code will be pretty much the same as if it will be generated with the equivalent Java program. And this at compile static annotation, using or annotating our code with this, we have tape safety, we are immune to monkey patching, and we have some performance improvements in some cases. And then with at compile dynamic, you can disable this static compilation. Imagine that you have a class and you annotate the class with compile static, but you have one method that is dynamic. So you can just annotate this one method that is going to be dynamic with this compile dynamic annotation, and you're done. And now, oh, come on. So with this, in this category, you have annotations to manage dependencies using Greach. Greach, it's a dependency manager embedded into Groovy, and with Greach, you can just get or quickly add some Maven dependencies into in the class path and just execute the code. It's, for example, you can use this to when you create a script. So we have this. The first annotation is at grab, and you can use here the standard Maven coordinates, the group, the module, and the version. And you, for example, you can always use this compat form. Then we have this grab resolver, because at grab only find for dependency into Maven Central, but sometimes you want to add another repository. So for example, you can add this grab resolver and add this Maven repository and just annotate then use this grab annotation. And with grab exclude, you can, for example, exclude some transitivity dependencies. And I think, okay. Now for the summary, I mean, I don't pretend that you remember all of this annotation. There are a lot of them, but I'd be happy if when you go home and you go to your work and the next week or the next month you are developing with Groovy, maybe you think or you say something like, I was at Iván's talk at Greach and I remember that he talked about this AST that we can use here. So you can go to the documentation and check the annotation and use it. So this talk is only to let you know that there are a lot of annotation that will help you in a lot of cases to improve your code or to write less code. So if you remember, and I'm going to finish with the same quote, the best code is not code at all. So please do not write code that it's not necessary to write. So, thank you very much. This is my contact information, my Twitter, my email, and my GitHub account. I'm going to push these examples of code to GitHub, and I'm going to upload these slides to SlideSet, and I'm going to tweet about it. And please, if you have 30 seconds, in this URL, you have an anonymous Google form to give me some feedback about this talk. So please, just let me know if you like the talk, if you think that it was crap. Say whatever you want because it's anonymous, so don't worry. And now if you have some questions, I think, yeah, we have time for questions. Some question? Anyone? Yeah? Yeah, so the question is there any relation between type check and compile static? Yeah. If you annotate your code with at compile static, it will also be annotated with type check. So it's a type check is something like a subset of compile static. Yeah. If you only annotate the code with a type check, you will have type check. I mean, the compiler will check for your types, but the code will be dynamically compiled, not statically. Another one? Okay, thank you very much.